Okay, so I just got a couple more things to talk about, and hopefully let you guys out early. So just worked out a couple of things here. So what we've seen so far is a process where you choose an algorithm that you want to start off with, and then you run through the process of tuning the parameters with the cross-validation set and figuring out what the test site accuracy is. So we do that for just one algorithm so far. So the usual practice that we do is we do this step with a few different algorithms that we learn, whether that's, do this process for logistic regression, do this process for SVMs, do this process for neural networks and so on. So we chose a few algorithms and we try to run through the above steps. And then what you do is we look at the test set accuracy of each algorithm. This is where you don't actually tune anything in the test set accuracy. It's important. So you use the test set to determine the accuracy of the final trained model that you have. And from all of these different test set accuracies that you have for every single algorithm, you choose the algorithm with the highest test set accuracy. So that's why it's important to split up the cross-validation and test, because the test is used to assess the final accuracy when you're done tuning everything. Okay? So when you want to create a cross-validation set, it's actually quite easy. You have a bunch of data which we decompose into a training and test set. With a cross-validation set, you're just decomposing your data further. So you have your data, and then you decompose your data into 3 different stages. So you have a portion of your data for the training, a portion of your data for the cross-validation, and a portion of data for the testing. So in practice, there are 2 acceptable breakdowns you can use that I've seen. So some people like to take 60% of their data as the training, 20% as the cross-validation, and 20% as the testing. So that's what people usually do. There's other people that like to do 50, 25, 25. So half of your training data is, half of your data is for the training. You find your, parameters there. 25 is for the cross-validation, and 25 is for the testing. So 60, 20, 20, or 50, 25, 25 is what I've seen. Some people like to do 80, 10, 10, but that's a little extreme. Because it doesn't actually accurately model the examples that you see in practice. So you want to have a good enough size for the cross-validation for the testing to be able to do your tuning. Okay? So this is what happens if you had a whole bunch of different algorithms to choose from. If you are restricted, you can only choose one algorithm. Let's say you're forced to use neural networks, or you're forced to use support vector machines. Then there's no need for a cross-validation set, because that set, its purpose is to be able to choose between different algorithms. So if you don't have a choice, then using just training and test is perfectly fine, because you're restricted to just one algorithm. So there's no need for a cross-validation set. Okay? So if you have no choice but to use one algorithm, okay, then there's no need for a cross-validation set. Okay, you can just do training and test. So if you have this particular situation, then there are 2 acceptable breakdowns. So 2 breakdowns possible that I've seen are something like this. So it's either, some people like to use 70-30 or 80 and 20. So those are pretty 2 acceptable ones. So we have 1. So there's 80% for the training and 20% for the testing. That's actually what I did for lab 3. And I think lab 2, that's what I did as well. I can't quite remember. But for lab 3, I for sure did 80-20. So by fluke, what we've done here is acceptable practice, because we're focusing just on one algorithm. Okay, but if we have several algorithms to choose from, then the cross-validation set is important. So you can use that to figure out which algorithm you want to choose in the end. Okay, so that's finished that topic. We're going to talk about bias and variance next. Bias and variance I covered very lightly when we talked about logistic regression with overfitting and underfitting, but I'd like to give you a formal definition now. Okay, so we have only talked about this in brief early in the course. Okay. So we're going to give you I'm going to give formal definitions. Will now be covered. Okay, so this is, so formula should not be covered. So there are 2 errors that we encounter in practice. There are errors due to bias. So what bias means is that it's the difference between the predicted output and the expected output, right? So for example, if you're doing linear regression, right, and the predicted output was 4.5 and the expected output was 5, then the difference is 0.5, okay? So we usually want the difference between the predicted output and the expected output to be low, which means that we want what's called low bias, all right? So do you find this is the difference between the expected output and the predicted output? Okay, so what we want is we desire low bias. So when your system suffers what's known as high bias, what that means is that when you predict certain outputs, the difference between the predicted and the expected are so large that this is probably a symptom of underfitting, right? So when we took a look at the logistic regression stuff, when you're underfitting your model, then you notice that the difference between what the predicted output gives you, what the expected outputs are actually quite high. And that's why we call this high bias, because the difference is actually quite high. Okay? So high bias means that there is a large difference between the predicted and expected outputs. Okay, so this is actually a symptom of underfitting, as we talked about before. Okay, so that's errors due to bias. Now what about errors due to variance? Okay, so the variance is defined, so let me just give you obviously we talked about before. The variance is defined as the variability of a predicted function, or the spread of a predicted value. So the variance is defined as the variability of a predicted output. Okay? So what this means is that usually what we want is we desire what's known as low variance, where if you have a particular input, you see a predicted output. If you change that input slightly, you would expect that the output undergoes similar small changes. Okay? So what it means when you have high variance is that when you put in an input, if you have a very small change, the output is actually going to have very large changes. Okay, so that's what it means by something with high variance. And that's actually a symptom of overfitting. If you actually take a look at those examples where the curves are actually very, very complex, if you change one of the features slightly, you'll see that the output varies widely than what it should be. So you want something with low variance, which means that any small changes to the input, you would expect the output to undergo smaller changes as well. If you have high variance, that means that the changes are actually very large, which is actually not desirable. Okay, so similar input training examples. Should give relatively the same predictions. Okay, and this is what we call low variance. Okay, so high variance means that when you change the input slightly, the output is going to change a lot, and that's not something you want. The slightest change of the input results in a very large change, output change. Okay? And this is what's known as high variance, and this is a symptom of overfitting. Okay? So just to put everything into perspective, here is a graphical representation of what all these symptoms are. Okay? So I actually pulled this from a nice person, his website. His name is Scott Fontman Rowe. And he has some very nice machine learning examples that you can learn. So the source is Scott Falk-Monroe. You can Google him up, or I can provide a link later. Okay, so here's a graphical representation. So imagine you're at a shooting range and there's a bullseye target in front of you. The red areas are what are the expected outputs, and the blue dots are what the predicted outputs would be. So for example, this would be the ideal situation where your predicted outputs match the predicted inputs. So they're all clustered within the same predicted output, and this is the ideal case. All right? Here's the case where we have high bias and low variance, which means that the outputs are so far away from the expected outputs, but there is very little variability between them. Okay? So this is a symptom of underfitting, right? Because most of the outputs are actually clustered all together nicely. There's very little variance, but the error between the expected outputs and the predicted outputs are so large. So this is an example of underfitting. Okay? This example here has low bias and high variance, low bias and high variance, which means that when you predict the outputs, they're more or less centered around where the expected outputs would be, but there's such huge variability when you change the input slightly. So this is overfitting. Okay? And this here is just a crappy model. Don't even, like, this is pretty crap. It's high bias and high variance, which means that not only is it there's a combination of overfitting and underfitting at the same time, which means that just start over again. It's a pretty crappy model. Okay? So this is just a very bad model. Okay? So this is a graphical representation. Okay? So the bullseye area, or the red area, is the expected outputs. Okay? The blue dots are the predicted outputs. So you want the predicted outputs to more or less be in line with the expected outputs, and you want the variability to be very small. So the top left corner is the ideal case, and the other three are the ones that you don't want. Okay?
So did he just attribute these to precision and accuracy? Or
Sorry?
Like, is this precision and accuracy? Precision versus accuracy, or do you know this is precision?
I'm sorry, I don't follow your question.
Because like, there's a picture like exactly like this for sensors.
Oh.
Precision versus accuracy.
Yes, correct. That's right. That's right. So precision means that all of them are pretty much clustered together, but the accuracy is off. And if you want high precision and high accuracy, then you want the top left.
So do we use those words, or just bias?
You can certainly do that. Yeah, for sure. Bias bias means that it's far away from the expected output. Precision, what that means is that precision, you can equate that to low variance. Okay, so precision means that when you change the input slightly, the output should also reflect smaller changes as well. So you can equate precision to low variance and accuracy to low bias. Okay, so that's good. Yeah. Okay? Okay, so let's just detour to neural networks for a bit. Let me just write a slide about that. So when you're underfitting in neural networks, what that is a symptom of is that you don't have enough neurons in the hidden layer. So underfitting can happen if there are very few neurons in the hidden layer. So if you have very few neurons in the hidden layer, what's happening here is that you don't have enough neurons to capture the variability of the data that you're seeing. All right? So not enough neurons to model behavior. Okay? Overfitting is having too many neurons. So there's too many neurons that, you're trying to spread the functionality or the variability of the data throughout many possible neurons that it actually does overfit. So overfitting is having too many neurons in the layer, in the hidden layer. Okay? So this is trying to spread functionality to too many neurons. Okay, so what you can do is you can use regularization if you want to prevent overfitting. So you can specify as many neurons as you want, and you can use regularization to try to compensate a little bit. So there's a little bit of push and pull. So we can use, I just wanted to put this in because it is a discussion question in the lab, and I figured I'd just put this in so you have something to talk about. So we can use regularization to prevent overfitting. Okay, you'll explore that in lab number 3. Okay. All right, so I've got a couple of more things to talk about, and then we're going to end today's talk. So question, here's a question that we haven't asked. When you're taking a look at your training set and your test data sets or whatever, how do you exactly know whether or not you have high bias or high variance? Like when we talked about the regression stuff, when we're fitting our model, we can visually see it, right? But is there an easier way to figure out whether or not you have high bias or high variance? Because what we're seeing now is we're just visually inspecting. But is there any concrete way to actually figure out whether or not you have high bias and high variance? And there is. So how do you figure out if we have high bias or variance? Okay, you use a concept called learning curves. Use learning curves, okay? So what learning curves does is that it examines the cost function as you change the number of training examples for your training data set. So what you're doing is you're plotting the errors for the cost function of the training set and the cross-validation set, and you're trying to take a look at where the points converge. And depending on how these converge, it'll tell you what the system is undergoing, if it's high bias or high variance and so on. Okay, so these examine the behavior of costs in the training and cross-validation sets. Okay, the cross-validation sets, as we vary the number of examples. Of training examples. Okay, so here are the steps that you do to create a learning curve. So the first step is we start with one example. Okay, when you start with this, what you're doing is you're going to find the best parameters. So one example in the training data. So you're going to find the best parameters with m is equal to 1 in the training set, okay? 2. Then what you're going to do is you're going to find this cost to use these parameters, okay, on this one example, okay, which is called JTrain, right? So this will be the cost to determine, or the cost used to get these parameters to be associated with your data, okay? So you have this cost, and then what you're going to do is you're going to use these parameters to find the cost over all cross-validation examples. Okay, which we'll call JCV of theta. So that's the cost to use those parameters that you use from the training stage and use that to figure out what the cost to be for the cross-validation stage. Okay? Yes?
Are we doing this one at a time?
Yes, but you're not going to do that for the exam. Don't worry. So what you're doing is if you have 100 training examples, you do it for 1, find the cost between them both, 2, find the parameters, find the cost between them both. So it's a very exhaustive process, but it actually will help you in the long run. So you write a program to do that, obviously. One example at a time. If what you do is you choose the number of features that you want, whether it's 3, 4, or 5, and then you vary the number of examples. So then what you do here is that if you see that there's high bias or high variance, then you change the model and then you run the learning curves again. Okay? So you plot them both. So this is assuming that you've decided how many features you have and the architecture and all that is set. So you're finding the learning curves for this set architecture. Right? So plot them both. and then repeat 2 and 3, and increase the total number of examples. Trying to finish up, hopefully 10 more minutes. For the training set until we until we exhaust all examples. Okay, so what you're going to do is you're going to start off with one, so you have some assumed model, you start off with one example, find the best parameters to fit through that one example. Use those parameters, figure out what the cost function is for using it for the training data and for the cross-validation for all the examples, and then you increase the number of samples, you repeat this until you exhaust all the examples. Okay, so these produce learning curves. Okay, for both, the training and cross-validation sets. Okay? Okay, so the way these converge, tell you whether there is high bias or variance. Okay, so obviously a picture's worth 1,000 words. Let me just show you a couple of pictures. Okay, so I pulled these from Andrew Ng's slides because they actually describe everything that I want to talk about. So instead of me redrawing it, I just took a couple of the slides. So, okay, here we go. So this is ideal case, source. Okay, so what we have here is we have 6 different examples. So what we're doing is we're introducing one example at a time, okay? Also, the model that we want to choose here is just the quadratic model for now. Okay? All right. So notice that M, so this is for the training set size. So we're going to vary this, and we're going to figure out what the costs are between them. So, for example, I start off with one example, and I find the right parameters. It might look something like this. It's very easy to find any, so there's lots of different parabolas that'll fit that one point. So when you actually calculate the cost for the training, it's obviously going to be very low because you found a curve that'll fit through that point exactly. So the error is going to be probably low, somewhere probably over here. So this is when m is equal to 1. And then, you know, you decide to increase the number and fit the parameters, so it might be something low here. This might be m is equal to 2. And then as you notice, as you start increasing the number of points, you'll notice that the error will start to increase more because you have a bunch of points where there's variability and there's only so many points that you can fit through a parabola exactly. So something might look like this, and then something might look like this, or something might look like that. There might be some error here, or there might look something like this. So the error, you know, this will slightly start to increase over time. So what this will look like is that it'll probably look something like this. It'll plateau towards like something like that. Okay? And then when you use these same parameters for the cross-validation set, what you're doing is you're cycling through every single example for the cross-validation set. So this is number of cross-validation examples. And then this is the cost for linear regression between them, you know, so this is the cost for the training and for the exam. So then when you're using these parameters at the very beginning, it's going to be very high because what's happening here is that this would technically be overfitting the data. So if you're using these parameters for the cross-validation, it's going to be very high like this. And then eventually, as you start increasing the number of parameters, it'll start to slowly converge like this. So something like that. Okay? So the characteristics here is that you have a large gap at the beginning, a kind of medium gap in the middle, and then a small gap towards the end. So this is the ideal case. Okay? So this here, this is the training, and then this here is the cross-validation. Okay? So the error is small as small when m is small, because we can get a good curve. to fit a small number of points. Okay, so that's pretty good. And then we do expect to increase it, we do expect the error to increase over time because you have a bunch of variability here, and fitting a parabola through all of them is probably not going to give you the best results. So this is the ideal case. You have a large gap in the middle at the beginning, a medium gap in the middle, and then a small gap towards the end. And then this is what will happen if you were to have high bias. Okay, so this is what happens. He decided to draw. So let's say we're fitting a linear model, okay? So as we start increasing the number of examples, you'll notice that the error is not likely going to change. The error is going to be very high at the very beginning, and then as you start increasing the number of training examples, the error doesn't really change. So the number, even though you have an increased number of examples, there's only so many points you can fit a straight line through. So the error is going to be very high at the beginning, and then it settles very quickly towards the end. So this is an example of high bias. Okay, so there's very high error at the beginning, so it also converges more quickly. Okay, and there's 5 training examples here and there's 13. So this statement is pretty good. So if you have high bias, what this means is that if you keep adding more examples, the error is probably not going to change and it's very high. So this is an example of underfitting, because you have so many errors as you're trying to fit the model through all of these points. All right, so that's a version of high bias. And then here's what high variance looks like. Okay, sorry, so this is high variance. And the model here was a 100th order polynomial, so it's something like that. So the training is sum from 0 to 100, and then okay, so something like that. X of to the power I. So there's 100. Okay, so if you take a look here, as we start, so let's say this is our model. As we start to increase the total number of examples, we'll notice that the error seems to be okay. But what's going to happen is that because we're overfitting, there's going to be actually a very large gap. So let's see here. So this is your training, and this is so as you start varying, the error seems okay, but there's going to be such a huge error with the cross-validation because you're overfitting. What's going to happen is that with these new examples in the cross-validation set, because there's high variance, when you change the input slightly, it's going to give you a very large error. So the consistency here is that there's actually a large gap for most of it. So there's a large gap for most of the curve. So you can address overfitting by perhaps adding more training data to your data set. So that might help with the high variance stuff. Okay? All right, so I've got one more topic to talk about, and then we're going to finish. The last and most important topic we need to talk about is what's known as skewed data evaluation. This is especially important when you take a look at medical diagnosis, because especially because you have data sets where the majority of the cases are negative and only a very few amount of cases are positive. So this is what's known as skewed data evaluation. Okay. So this will probably take about another 5 minutes and we're going to quit here. So far, we have used classification accuracy to assess performance. Of our algorithm, right? So we've used that. So all you're doing is you're checking to see how many of the labels matched with your test set from the predicted labels. Okay? So this assumes that the data that we have has a pretty good amount of spread in terms of positive and negative. So there's a nice spread of positive examples, and then there's a nice spread of negative examples. So we assume that there's a good amount for each class. Okay? So the data we have seen assumes a good spread of positive and negative examples. Okay? So sometimes we have what's known as skewed data. This is very important in cases where you have very few positive examples or very few negative examples and a lot of the other. So the number of examples for one class is much, much smaller than the other class. Okay? If you have skewed data, then classification accuracy is not a suitable assessment, performance assessment for your algorithm. So classification accuracy is not a suitable performance metric. On skewed data. And I'm going to give you an example to outline, so to make this rather obvious. Okay? So here's an example. So let's say we have 1 million patients and data to determine if a patient has cancer. So in this case, our training set is 1 million. Okay? And then let's say for the moment that only 5 examples are positive. Okay? So that means that 5 examples are positive and 909,995 examples are negative. Okay? So let's say we had a prediction algorithm where we just said everything is cancer-free. Right? So for example, so instead of looking at the features, we'll just say that everything is cancer-free. So this means that you predicted the 999,995 examples correct, but the other 5 are incorrect. So what would be the classification accuracy? 99.5%. Right? So you look at the classification accuracy and you say, hey, this looks like a pretty good system, but you classified all the examples that are positive wrong. So that's not really a good indication of classification accuracy, right? Because you classified all the positive examples as wrong and all the negative examples as right. But all the negative examples outweigh the positive examples, so when you actually calculate the classification accuracy, you get around 99%. So it gives you a false sense of hope that you're actually doing pretty good, but you're actually classifying every single positive example wrong, which is probably not the best thing to do, right? So, okay, let's say, so to determine a patient with cancer, so we'll call y is equal to 0 benign, and y is equal to 1 malignant. Okay, so let's say our prediction algorithm almost done. Prediction algorithm was y equals 0 for every example. Okay? So what you're doing is you're ignoring the features. Okay? So what you're doing is you're saying that every tumor is benign. So what's the classification accuracy? Well, it's 999,995 divided by a million, because you got all the other examples right except for the 5 that matter. And what's this? It's about 99.9995%. So if you had no context, you'd be like, okay, this is a pretty good algorithm. But if you don't know that the data is skewed, then it actually will work against you. If you know that the data is skewed, this will tell you that the algorithm sucks because it didn't classify any of the positive examples correctly. All right? So we get all of the positive examples wrong, but the accuracy is 99%. That's pretty bad. That's not a really good indication. If you have skewed data, that sucks. Okay? So what we're going to do is we're going to use another measure of accuracy. We will use another measure of accuracy. Okay? we're going to use two new terms. We're going to use what's known as precision and recall to assess performance. Okay? So these vary, so these values are between 0 and 1. Okay, they're between 0 and 1. So we're going to use two terms, precision and recall for skewed data. Okay? So the definition of precision and recall are very straightforward. So precision is the following. So let's say you did a set of predictions. Okay? Out of all of the predictions that you made that were positive, how many of those predictions were right? How many of them were actually positive? That's the definition of precision. Okay? So out of all predictions made, okay, that are positive, no, positive, how many are correct? Okay? Recall is something related. Recall is, out of all of the examples in the training set that are positive, how many did you classify that were correct? So precision is localized, where out of all the predictions you made, how many of them are positive and correct? And recall is out of the entire data set where it's positive, how many of them are correct? Okay, so out of all examples in the training set, okay, that are positive, that are y is equal to 1, how many predictions are correct? So that's recall. Okay? To help us calculate recall and precision, we're going to create what's known as a confusion matrix. It's a little bit of a misnomer. It's actually a really good thing, but at hindsight, it's pretty bad. Okay? So let's see here. Okay. So recall and precision. Actually, I'm going to do one more thing. So the higher precision and recall are, the better the performance. So we'd use recall and precision here on skewed data, not classification accuracy, unfortunately. Okay, so here's so we're going to create a confusion matrix, and we're going to talk about one more thing here, and we're going to call it a day. Okay, so to help us calculate precision and recall, create what's known as a confusion matrix. Confusion matrix is very simple. It's going to be a 2x2 it's going to be a 2x2 matrix. Okay? So here are the predicted, here's the predicted output, and here's the actual output. Okay, so let me just, okay, so y is equal to 1. Okay, so we can split this up into a 2x2 grid. So if the predicted output and the actual output are the same, this is what's known as a true positive. So this is a number of true positives, which I'll call TP. Okay? If the predicted output is positive, but the actual output is negative, this is what we call a false positive, which means that we predicted the outcome to be positive, but it actually is not. Okay? So this is what's known as a false positive. So this is saying that, hey, you got cancer, but actually they don't. So it's actually, pretty shitty to mess with their head that way. Right? So this is a number of false positives, FP. If the predicted output is false, but the actual output is true, we call that a false negative, because the predicted value is saying, hey, you don't got cancer, but you actually do, and that's pretty bad too. All right? So this is the number of false negatives, or FN. And then finally, if you predict false and the actual output is false, and those are the number of true negatives, right? Because they actually match up. Okay, so this is FP. So no, sorry, true negatives. Okay? All right. So that's good. So what we want to do is, this is good. So if you want to calculate precision, right, what you do is you calculate the number of true positives. So what you do is you calculate the number of true positives divided by the, let's see, number of true positives plus false positives. So what this number here is, this is the number of predicted positives, right? Because if you have the number of true positives and the number of false positives, you predicted that they're both positive. So the number of so TP plus FP is the number of predicted positives. Okay, so that's precision. And recall is basically the number of true positives divided by the total number of actual positives in your example. So true positives plus false negatives. Okay, so this here is the number of actual positives. Okay? All right. So, okay, let's see here. So I got one more thing to talk about, and we're going to call it quits. So this will only take a couple of minutes. All right, so there's all these different precisions and recalls, right? So how do you actually, so let's say you have a bunch of different algorithms that produce, different precisions and different recalls. How do you actually measure them so that you have one combined score that tells you whether or not the precision and recall is accurate? Because you'll have one algorithm that has one precision and one recall, and another algorithm that has another precision and recall. So there's got to be a way to combine both of these numbers together so you get one final score that tells you what the performance would be. And we call that score the F1 score. Okay? So to decide whether the algorithm performs well, this is my last slide here, we combine both to produce the F1 score. Okay, so the F1 score is defined as twice times the precision versus recall and the precision plus. So if P stands for the precision and R stands for the recall. Okay, so this also varies between 0 and 1. Okay, so this means that this is a bad system, and this means that it's a good system. Okay, so if any one of these numbers is 0, then the score is going to be 0, and if any number of these are 1, then the score is going to be good as well. So let's see here. So 2 twice. Yep. So if P or R equals 0, then the F1 score is 0. And if P or R is equal to 1, then the F1 score is going to be 1. Okay? Yes. Yep. Or one of them, yep. P and R. Okay, whatever. But yeah, it's fine. Okay. And I think that's, so the better the F1 score, that's it. So the better the F1 score, the better the performance. Okay, let me just highlight this. And that's it. Okay. All right. And that's all I have for you today. Okay? All right, so next class, we're going to talk about something really, really exciting. We're going to go into unsupervised learning. So we're going to talk about how to actually extract groups from data which actually have no labels to begin with. So this is actually the trend in data science right now, and we're going to start that talk next class. Thanks for coming.